So we were discussing how to find the shear stress distribution in a rectangular cross section. As you can see here, first you should well define your height. So sometimes maybe they can call this distance h, then the whole height will be 2h. Then you will develop a formula based on the figure. In this figure here, they considered that the whole length is h, okay? So the whole height is h, then c, which represents the distance from neutral axis to the top, is h over 2. Because here we know that for a rectangle, c1 equals to c2 equals to h over 2. So c is simply h over 2 here. And we have b is the thickness or width, so which is here equal to b. It can be any value. We'll develop the shear stress distribution function of these parameters, function of b, h, the shear within the section v, and the area of the cross section. Okay, so to start with, let us go back to the formula. If we do a cut at any location from the neutral axis, and we want to determine the shear stress along this section, then we should apply the following formula. Shear stress equals to VQ over IB. Keep in mind that V is the shear in the cross section that we can get from the shear and bending moment diagrams. I is the inertia of the whole section, not only of this part. So I is for the whole rectangle about its neutral axis. Here we are considering the case of transverse loading, creating, if you want, shear stress perpendicular to Z. Okay, so this will lead to a neutral axis defined along Z. Okay, and then we know that the neutral axis should pass by the centroid of the section. So this is our neutral axis in this case. Under the effect of this type of loading, we'll have that the shear stress distribution will follow a parabolic profile, as we'll demonstrate now. So we'll apply this formula, VQ over IB. The shear, as we said, is perpendicular to neutral axis. The neutral axis is passing by the centroid of the cross section. Inertia I represents the inertia of the whole rectangle about the neutral axis, which is BH cube over 12. And concerning now what is Q, we should determine the value of Q. To determine Q, it's the area of the part of interest. So here we did a cut here. We did a cut here, so the area is above this level. You can take also the area below, because we have demonstrated that Q equal to minus Q prime because of action reaction. So here we are developing for any position, what will be Q? We'll take the top, in this analysis, we'll take the area above the section. So for this area here, Q is defined as A prime times Y bar. So first we should define A prime. To get A prime, we have just to determine the height of this rectangle, and the width, of course, here is B. Concerning the height, it's simply the difference between this distance, which is C or H over 2, minus this one, which is the distance from the neutral axis to the cut. So this distance will be C minus Y, and we can replace C by its value, which is H over 2 minus Y. Now, concerning Y bar, which is the coordinate of the centroid of this area, of course measured relative to the neutral axis. So Y bar will represent the distance from neutral axis here to C prime. This is the distance Y bar of interest. To get Y bar, all we have to do is to say we can decompose it into two parts. you can do, or you can say it's equal to this distance, which is y, plus the distance from this level to this one, which is c minus y over 2. Or you can say also in another way, it's the whole distance c minus this part. So both will give you, of course, the same result. Okay. So if we consider y plus the first approach, yani y plus this distance, then we can say that y bar is equal to y plus this distance is c minus y over 2. So we divide this by 2. So plus c minus y over 2. Then we get that y bar is equal to y over 2 plus c over 2. So you can take 1 over 2 into factor, and you will have that y bar is 1 over 2 times y plus c. And you can, of course, replace c by h over 2. So this will give you the value of y bar. Now, to obtain a q, you just have to multiply y bar by a prime. So you get b over 2 times c plus y times c minus y, which is c square minus y square. So the first moment will vary with y, as you can see, and it's equal to half b c square minus y square. Now, as expected, q is 0 on the top. So on the top, the value of y is equal to c. So if you take this level, at this level, y equals c, and we have seen together last time that at the top surface shear is 0, and this is expected because the first moment about the neutral axis is 0, since you don't have any area above this level. So if you can verify this from the equation. If you replace y by c, c square minus c square will give you 0. And the maximum first moment will be at this level, because when you are at the neutral axis, you will have this whole area above it. This is the maximum possible area above the neutral axis, which will give you q max. So q max will take place at y equals 0, so at the neutral axis level. This is why we will expect here that the maximum stress will occur at the neutral axis, in opposition with the normal stress, because in the normal stress, we have that when you have pure bending, the normal stress is 0 at the neutral axis. So now we are ready to replace into the expression of tau in order to get the distribution of shear stress in my cross section. So I know that tau is V times Q over IB. Let me replace. So first, V is the shear in the cross section. As we said, we get it from the from the shear and bending moment diagrams. Once I get V, I have to multiply it by Q. Q is 1 over 2 times B times C square minus Y square over the inertia. We said that we take the inertia for the whole cross section about the neutral axis. We know that for a rectangle, it's BH cube over 12. So times BH cube over 12 times B times B. Now we can start to simplify. You have B and B will cancel out. Here you have 2 over 12. It's 1 over 6. You can take it to the numerator. It's 6. So it's 6V times C square minus Y square over BH cube. We can now simplify it a little bit more. So we can write that tau is equal to 6V times, here we'll take C square into factor. So if I take c square into factor, I get c square factor 1 minus y square over c square. And for bh cube, I can decompose it into bh, which is the area of my rectangle, times h square. So bh is the area of my rectangle A. And I have that c represents h over 2. So I can replace c by h over 2, or if you want here, instead of h square, I will put 4c square, because h is 2c. Then c square will cancel out, and I will end up with tau equals to 6 over 4 can be simplified to 3 over 2. So tau is 3 over 2 times v times 1 minus y square over c square over the area. Okay, so this is the formula. We derived it together. Why I included a? كان فينا اترك a function of b, h, etc. But I want to compare. I want to do this to compare with the average stress. Okay, the average stress. If you want to calculate the average stress in this section, what do? You can say that the average stress is just equal to V, which is the total force in the cross section, the total shear force, over the area, So it's over A. Now we want to compare here what is the ratio between tau average and tau max. So when we did this simplification, we can see that this is the expression of, this is tau maximum. Tau max is 3v over 2a. So we can say that the maximum shear is 3 over 2 times the average shear. Okay, because here v over a will represent tau average in the cross section. Okay, so tau max is 3 over 2 times v over a. Let us do some examples on how to calculate shear and shear distribution. So if we start with the following example, we have 3 full-size 50 times 100 millimeter boards that are nailed together to form a beam subjected to a vertical shear of 1,500 newtons. It's very important to know the direction of the shear. You can have shear in the vertical direction. Then the neutral axis you consider is perpendicular to the shear is horizontal. But also you can have another scenario. You can have horizontal shear. If you have a horizontal shear, then in this case your neutral axis will be vertical. So the shear you will consider is perpendicular to the neutral axis. Okay. Here, since the shear is vertical, equals to 1,500 Newton, then the neutral axis I will consider is horizontal, and it should pass by the centroid of my cross section. Since my cross section is rectangular, then this is my neutral axis. Now, knowing that the allowable shearing force in each nail is 400 Newton, determine the largest longitudinal spacing S that can be used between each pair of nails. So here we have several parts, several boards, okay? Before we put the nails, they can slip relative to each other. So if you apply the shear load, as we have seen in the course material, if you don't have any bond, or if you are not relating the parts in any way through nails, or uh, by let's say adhering them together, then you will have possible slipping. You will have slipping between them when you apply the shear. However, when you put nails, for example, this tendency to slip will be opposed by the nails. So the nails will develop shear stresses to oppose the tendency of slipping between the different bones. So the shear stress here will be all carried by the nails. Okay. This is why here we should know the capacity of the nails in order to design the system. So they said that the allowable shearing force in each nail is 400 Newton. Based on this, we want to determine what is the largest longitudinal spacing S that can be used between each pairs of nails. So you can see here that the design here is to define what is the spacing between nails. To do this, we should know how much force is carrying each nail per unit length. Okay, so if you consider a small analysis, you have here a repetitive pattern. You have a repetitive patterns for each distance as you have two nails, and this means that each two nails, okay, will take care of this part of this part. Okay, so if I take from here s over 2 and from here s over 2, so it will carry the load developed, okay, the force developed for a length s. Okay, so the strategy will be to determine first what is the force per unit length developed due to this shear. So this shear will induce, if you want, as we have seen together, we can find the corresponding shear flow in Newton per meter. And this shear flow will be carried for a distance s, will be carried by two nails. Okay, so the strategy will be first to find what is the shear flow. And once we find the shear flow, we can determine what should be S to not exceed the maximum capacity of each nail. So let us start first by saying how we determine the shear flow. We go back to the formula. The shear flow in Newton per meter is VQ over I. Okay, so now going back to our figure, this shear flow to be determined at any location is to take a certain cut, okay, and find the first moment of the area. Now here how to choose our cut? We should select it in which way? If we go back to our figure, we should look at the level where we have the nails, because the nails will oppose this shear flow. And as you can see in the figure here, your nails are attaching these two parts, so the plane of shear will be this one. Okay, for the upper and lower part you have symmetry. This is why you can do the analysis for one part only. Okay, so if I consider here the upper part, the upper two nails are connecting these two boards, so they will resist shear stress developed at this level. And you know that the neutral axis is at the center, passing by the centroid of your rectangular cross section. So since the whole length here is 150 millimeter, and therefore from the top to the neutral axis you have a distance of 75 millimeters, then you can say that the distance here, you can find the distance between the neutral axis and your section, since the height of your part here is 50 millimeters. So this is 50 millimeters. And therefore, from the cut to the neutral axis, you have 75 minus 50. So this distance is 25 millimeters. We'll illustrate it now in a clearer figure. So now if I represent my cross section, as we said, the nails will carry shear at this level, which is at 50 millimeter from the top. And we have from the top to the neutral axis 75 millimeters. So this is 25. Now, all we have to do is to apply our formula. Okay, here this is the area of interest. The area of interest has a height of 50 and a thickness of 100. So you can keep units. If you keep units here in millimeter, just pay attention at the end in the formula to convert back everything to a meter. Okay, because you have your shear is defined, your shear is in a Newton. And if you keep everything in a millimeter, then you will get your shear flow in Newton per millimeter. So you can keep them in millimeter, but pay attention that then the shear flow will be in Newton per millimeter. If you want it per meter, then convert all your areas and Q to a meter, to meter unit. So we said A is 100 times 50. Now concerning Y bar of this area, so we take the distance from neutral axis to the centroid of this area. Since it's a rectangular area, here the centroid is at 50 millimeter from the top. And we know that the whole distance from top to the neutral axis is 75. So we can say that from the centroid of the cross section to the neutral axis, we have 55 millimeters. Okay, so now all we have to do then is to consider, sorry, here this is 25. The distance from here to here is 50 over 2, it's 25. Okay, and then this distance is 75 minus 25, it's 50. So Y bar is equal to 50 millimeter. And then now all we have to do is to multiply Y bar 1 by A. And then we get the value of the first moment, Q. Now, once we find Q, we are ready to find the shear flow, which is in Newton per meter. It's the flow per unit of length. Okay, the force sustained, the shear force sustained per unit length. Why here we didn't calculate tau, we calculated the Q, because here, as you can see, you have nails, and your nails will be spaced within a distance S. So you need to determine what is the shear to sustain per unit length in order to find the value of S. Okay, if you did the analysis per unit area, it's not a problem. But then, and if you found tau, which will be in Newton per meter square, then you will say that I will consider then the area carried by each two nails is this one. So this is equivalent because you will multiply again by the thickness, and the thickness will be simplified. Okay, so here, because of this, they directly computed the shear flow per unit length. The shear stress will be in Newton per meter square. And then if you do the analysis of shear stress, you say that the two nails are carrying shear in this area. While if you do the analysis in shear flow Newton per meter, then you say that each two nails will carry shear along this length, which is S. and both are equivalent because at the end the value of B here, which is 100 millimeter, will cancel out. Okay, because if you compute shear instead of shear flow per unit length, so you will have here IB. Okay, and then you will say that each nail will carry the shear over the area, which is B times S. So then B will cancel out. Okay, I will show you this in the equation. So if we are considering the effect of nails, we said we have two nails. So each two nails will carry shear per unit length times the length, the repetitive length S. So you can write that if you computed the shear flow in Newton per meter, so each two nails will carry Q times the separating distance between nails, which is S. And since you have two nails, this should be equal to 2 times F of nail. If you found the shear stress tau instead of the shear flow Q, so you can say that tau times the area of shear carried by each two nails. The shear area carried by each two nails is S times B. Okay, but what is tau? Tau is equal to VQ over IB, so it's Q over B. So you can replace then tau by Q over B, and since you are multiplying by the area, which is SB, as you can see, B will cancel out. So both analysis will give you exactly the same result, equals to 2 times the force developed by each nail. Since we know the capacity of each nail, the maximum capacity, if you want to get, if we want to design on the critical case, okay, then we'll consider F maximum, and this will correspond to the maximum possible distance separating the two nails. So we can say that S is 2 times F max, so S maximum between putting the nails, you have a repetitive patterns of putting two nails. S maximum is 2F over Q. We have calculated Q, they gave us F max, so we can find what is the maximum distance where we should put two nails again. So as you can see here, each S you should put two new nails to not exceed the capacity of your nails. Another problem. For the following beam and loading shown, consider an N section and determine the largest shearing stress in that section and the shearing stress at point N. So as you can see here, they can give you a beam subjected to any type of load. Here the load is relatively simple. You just have a transverse load of 10 kilonewton. So even no need here to calculate the fixity reaction, because you can do a cut at the section of interest and say due to equilibrium condition, here the shear force should be up and should be equal to 10 kilonewton. Of course, you have a bending moment also, but since they only asked about shearing stress, we don't care for normal stress here. We just have to calculate V. Okay, so the shear value in this section is 10 kilonewton. And now, once we determined V in this cross section, in order to get the largest shearing stress, we know that the largest shearing stress will take place at the neutral axis. So since we are considering vertical shear, the horizontal neutral axis is horizontal, and it's due to symmetry, it's passing here at the middle of our section. So this is 75, 150 over 2. This is 75 millimeters. So this is 75 millimeters. Now, the maximum shearing stress will take place at the neutral axis level. Okay, so then if you want to find the maximum shearing stress, we should take this area, the whole area above the neutral axis. And this area can be decomposed into two parts. You have a thin rectangle here and a larger rectangle here. Okay, so now you are already familiar with how to get inertia of such shapes. Will calculate together its first moment about neutral axis. So as usual, okay, in your formula of tau, you have dq times dq over it. I is the inertia of the whole section. So the first step will be to get the inertia of the whole section about the neutral axis. So to do this, we have practiced a lot on this in previous chapters. So all you have to do, you have to decompose in a simple way your geometry. Like here you can decompose it in several methods. You can take two rectangles here, 1, 2, and 3. This is a possibility. Here, what they did here is another approach. They considered a big rectangle and 4 small rectangles. Also, it's possible. This is a good, you can say that because these 4 rectangles are equidistant from the neutral axis, so it's enough to get the inertia of one of them about the neutral axis and multiply by 4. So this is what they did. For rectangle 1, since the neutral axis is passing by its centroid, you don't have to apply the parallel axis theorem. So for 1, I1 is 1 over 12 B1 H1 cube. Now, for these 4 rectangles, we'll take one of them and multiply by 4 because all have same area and all have same distance from neutral axis. So here, all we have to do is first to get the area of this rectangle, to determine the distance from the center of this rectangle to the neutral axis, and we apply the parallel axis theorem. So if we consider this is H2, this height is H2, we have all dimensions, we'll get them now from the figure. This is B2. So first we do 1 over 12 B2 H2 cube to get the inertia about this axis, the axis passing by the centroid of this rectangle. And then we apply the parallel axis theorem to get the inertia about the neutral axis. So plus A2, which is B2 times H2, times B square, which is the distance from the center to the neutral axis. Let us get the values going back to the figure. Going back to the figure, B2 is this thickness, okay? So B2, to get it, we just have to say that it's this whole distance is 200. So 200 minus 100, it's 100 over 2 because you have 2 parts from these 2 sides. So it's equal to 100 over 2, so 50. This is 50 and this is 50. Now concerning, so this is B2. Concerning H2, this is H2. H2 is 12 millimeter. And now, in order to determine the distance, the center of this part is at 6 millimeter from the top, 12 over 2. So this distance is 6. And we know that from the top to the neutral axis, you have 75 millimeters. So this distance in the parallel axis theorem is 75 minus 6, so it's equal to 69 millimeters. Okay. So now all we have to do is to replace in the formula. Then we get the value of the inertia. Now next step, you have that you want to calculate the first moment of this area about the neutral axis. And we said since we are computing the maximum shearing stress, then we should consider the area above the neutral axis, the whole area above the neutral axis. This is the neutral axis level. And we said that from neutral axis to the top, we have 75 millimeters. Now, we decompose also this area to get the first moment. So we know that for each area, the moment is A times Y bar to the neutral axis. So first, if we take this is area 1, this area is a rectangle. We have that the height is 75. We have seen together that here from the figure, this distance is 100 millimeter. So the area is 100 times 75. And we multiply the area by y bar 1, which is the distance from the centroid of this area to the neutral axis, which is 75 over 2 equals to 37.5. In this way, we get the first moment of area 1 about the neutral axis. We should add, we have here these two small rectangles. For these two small rectangles, you have same Q because they have same area and same distance from neutral axis. So all you have to do is to do 2 times area 2 for each part. We already computed area 2 before. It's 50 times 12. And concerning the distance from the centroid here to the neutral axis, also it was already determined in the calculation of I, so it's 69. And then you add both to get the total first moment of this area about the neutral axis. Now you have everything. You are ready to calculate your maximum shear stress. At this level, you have a thickness of 100 millimeter. So tau max is VQ over IT. Replacing all your variables by their corresponding values, you get tau max. And just also pay attention for units. If you want to get tau max in Pascal, so V is in Newton, Q, pay attention to transform Q to meter cube, I is in meter 4, and T is in meter. Then you will get your tau in Pascal. And now, next step, they told us to calculate the shearing stress at point A. So at point A, which is not on the neutral axis. Then to do this, I should do the cut at A. So I do my cut at A. Then the area of interest will change. This will be my area now. And I can expect that the shear, of course, will be lower than tau max because I am above the neutral axis now. So all I have to do is the same procedure. Now this is my area of interest. I decompose it into, I can decompose it as I did before into 3 parts because these two are identical. Or you can decompose it into rectangles, the thin one here. So you can say I can take this rectangle and this one. All strategies will work. You can do the decomposition as you like. Okay. So here, V of course is the same in the formula. It is the shear in the section, which is 10 kilonewton. You have Q will change. Okay, Q will change. Now we'll calculate it, but the other parameters, I, which is the inertia of the whole part, will remain the same, of course. And since the thickness here is still 100 millimeter, so also T is the same. So only what changed now is Q. I will calculate Q of this part. The calculation is similar to the one before. Just I have to change the values of heights. Okay, so already for this part, the calculation is similar and it's the same part. You can take advantage that you have already calculated this part in the previous calculation. Now, just instead of taking the whole rectangle to the neutral axis, you will take this one. So this will constitute your change. For this part, here, this is the rectangle that you should consider. Because if you divide like this, for these two Already you calculated the first moment, so you can directly replace. But now you still have to get the first moment of this rectangle instead of the big one to the neutral axis. So for this rectangle here, you should do the parallel axis theorem. You have that you have here, this is H3, let us call it. H3 is 40 millimeter. You have this part is 100 millimeter. So you can now compute the area. And you should multiply by y bar. So this is the neutral axis. Your neutral axis is at 75 millimeters. So now you should take the area of this part times the distance from its centroid to the neutral axis. Since you have 40 millimeter here, this means that the distance to the top is, from the centroid to the top, is 20. So you have to do 75 minus 20 equal to 55 millimeters. So now you have everything. You can calculate Q of this part. So as you can see, if you compare calculations, this term will remain as it is because it's the same area, while this one will change. Okay, this one was the whole rectangle to the neutral axis level. Here we just considered this part. So as we said, it's 100 times 40, which is the area, times y bar 1, which is 55. Now you get a new value of Q. As we discussed before, T, I, and V will remain the same. So you can calculate the shear stress at A, and of course you can verify that it's smaller than tau at the neutral axis. Another problem. For the beam and loading shown, determine the minimum required width B, knowing that for the grade of timber used, sigma allowable is 12 megapascal and tau allowable is 825 kilopascal. So here, if you want, we combined chapter 5 and 6. So whenever we do a design, we should make sure that all limit stresses are not exceeded. Normal stresses and shear stresses. And we know that a transverse load will lead to development of shear forces in the cross sections and bending moments. So whenever we do a design, we should make sure that we don't have rupture in any mode. We should not have rupture with respect to normal stress, and we should not have rupture with respect to shear stress. So we should not exceed the allowable normal and shear stresses of the material. Now, what is the strategy in such problems? First, of course, we draw the shear and bending moment diagrams. From these diagrams, we determine what is the maximum bending moment exerted on our section and what is the maximum shear. And if you remember, we discussed strategies before. If you have here C1 equals to C2, okay, and they didn't differentiate between tension and compression. This is why it's to get your it's enough to get the maximum moment in absolute value. Okay. However, if we have C1 different than C2, we should pay, and we have that sigma compression difference and sigma tension, we have to take care of different values of M. So we can calculate 4 values of M and select the minimum between these values. Okay. And here, what we should do first, okay, here we should consider first, as we said, the shear and bending moment diagram. The design criteria here is not to select the maximum or the maximum possible moment. The maximum possible moment will be taken from the diagram because we have all values given. But what is critical here, what we want to determine is the minimum required width. So this is our design parameter. Okay. Then we'll say, first, we'll consider the critical section where we have maximum moment, maximum shear. And at this critical section, we should make sure that we are not exceeding tau allowable and sigma allowable and tau allowable. So we'll get two possible values of B, okay? And then because we are trying to find the minimum required width, of course, we'll select the largest value between the two values of B we get, okay? So here, what is the design parameter will be the minimum required width of the cross section. Let us start by drawing the shear and bending moment diagram. So as usual, you know well how to do this. The first step will be you can calculate your reactions. You have a pin here, you have a roller here. So you can calculate first AY by doing sum of moments about D. Once you get AY, you do sum of Y equals to 0, you get DY. And since no load in X, AX is 0. Now, the shear and moment diagrams here are relatively simple because you have only concentrated forces. So to draw your shear diagram, you have just constant values, okay? And you can select from this shear diagram so we start as usual by plus AY. Then you don't have anything from A to B. At B, you have a concentrated force downward of 2.4. So you have a downward jump from 2 to minus 0.4. From B to C, you will maintain constant shear. Then you will have a jump of 4.8 kilonewton, which will lead to minus 5.2 kilonewton. And then you have an upward jump at D because you have the roller. And finally, you can verify that at E, the concentrated force, the downward concentrated force will bring you back to 0. So from this shear diagram, the critical section of shear is the one between any section between D and E is critical because it corresponds to the maximum shear developed. So Vmax in absolute value is 7.2 kilonewton. Now I will draw the bending moment diagram to determine the maximum bending moment in absolute value. So here, as you can see, since V is constant, M will be linear in this part. Then you have, at this level, you have a decrease because V is negative. And since all values of V are constant, you have linear variation in moment. But at jumps, you have sudden change in slope. So at B, you have the moment was increasing. Suddenly, it will decrease because of this sudden jump of shear. Then at C, it's still a negative moment, but it's steeper. So you have a steeper decrease because the slope now is 5.2 instead of 0.4. And you can use the area method here to determine the values of your bending moments at different points. Now, as you can see, because we are, as we said, there is no difference between C1 and C2. So I don't have to differentiate between maximum positive moment and maximum negative moment. And sigma compression and tension also were not differentiated. So I just care for the absolute value of the maximum. So I take just 3.6 kilonewton meter. Okay. So now I can say that this is my critical section in bending moment is the one corresponding to the value of 3.6 kilonewton meter. Now I determined my critical sections in shear and in moment. As you can see here, the most critical then will be, of course, section passing by D, because we have already seen that at D you have the maximum shear. Between D and E you have the maximum shear, and at D you have the maximum moment. Then you can say that the section at D is the critical section, because at this section you have at the same time maximum shear and maximum moment. In case you have at different locations, you should determine which criteria is more, if you want, critical. How? You will take for each case what is the value of B required, okay? And then you select between the two, you select the maximum B between the two to be on the safe side. But here we can be sure that the critical section is at D because it involves the maximum moment and at the same time the maximum shear. Okay, if we have them at separate locations, it's not a problem. We should do the calculation to determine which is more critical, the reaching the maximum bending moment or reaching the maximum shear. Okay, how to do this? Now we should do the analysis first to determine B minimum to not exceed the maximum bending moment. We can use the formula from previous chapter, from chapter 5, that sigma is m in a certain section is m over the modulus of the section S. So, and if you, as we know, S can be defined function of I and C. S is I over C. And for a rectangular cross section, we have demonstrated that I over C is BH square over 6 because it's BH cube over 12 over H over 2. So it's BH square over 6. And the minimum possible value of S is equal to M maximum over sigma. And then from this calculation here, you can just have to replace first M maximum by its value. Sigma allowable is given, so we replace it. Then we get what should be the minimum value of my S, my modulus S. Because if I reach this minimum, then M will be maximum. And if I go below it, okay, if I go below this value of S, I will have larger, I will exceed my capacity because I will have an allowable stress that should be larger than the one that can be sustained by the material, and this will lead to failure. Okay, because as you can see in this equation, M, we selected already the maximum moment. The maximum moment is now fixed. Okay, so I considered the critical section where M is maximum. Now, what will happen is that if I reduce S below the minimal value, the sigma will exceed the allowable stress. Okay, so S minimum will correspond to sigma equal to sigma allowable. If I reduce S more, then sigma will increase in this section and will be larger than sigma allowable, which will lead to failure. So now I can, by replacing M max by its value and sigma by its value, I can get the critical, I can get S minimum. And once I get S minimum, I can get the value of B because H parameter is imposed, so I can play with width B. So I can get the value of B minimum, which is 80 millimeter from the first analysis. Now, I should say that this is the criteria to not exceed the allowable stress, normal stress. I should see also what should be B minimum to not exceed the allowable shearing stress. So when I do shearing stress analysis now, I will use chapter 6. From chapter 6, I know that the maximum shear stress occurs at the neutral axis. Okay, so here I have a cross section that is rectangular. Because my cross section is rectangular, I know that I can use, if you want, the formula developed in the course material. I know that the maximum shear stress will take place at the neutral axis, and we already developed that for this case. What is tau max? Tau max is 3/2 times V over A. So you can apply that. You can apply directly this result because you have a rectangular cross section. Now V is the maximum shear, as we said. Okay. And concerning A is the area of the cross section, which is 150 times B. So now you have A function of B, so you can express B function of tau maximum. Tau maximum is the maximum allowable shear stress is 825 kilopascal. So if you replace in your formula, you can get the minimum possible value of B to not exceed the shearing stress. So as we discussed, it's we have just to replace in the formula. We said that the maximum shear is 3 over 2 V over BH, and this maximum shear stress is given here. The value is given, so we can determine what should be B to not exceed this stress. So the minimal value of B to not exceed this shear stress is 87.3 millimeter. So of course now, since you got two minimums, you will select the largest one because to satisfy both criteria. So B1 minimum should be smaller than 80. So should be larger than 80, sorry. Okay. And B2 minimum should be larger than 87.3. So to satisfy both criteria of B minimum, you should take the largest between the two values. So you can say now that B should be larger than 87.3 to satisfy both criteria. And then we can say that what is more critical here is the shear stress, okay, not the normal stress, because you will reach failure in shear before reaching failure in normal stress, okay, because for the normal stress you can go below 87.3, you can go until 80 without failure. However, in shear stress you cannot allow values of B lower than 87.3. So here the shear is more critical than the normal stress. Another example, for the beam and loading shown, consider section NN and determine the shearing stress at point A and the shearing stress at point B. So in this example, first they gave us a beam with a certain load, and they asked for a specific section, okay? Sometimes if they don't mention the section, they just say, for example, consider the maximum possible stresses in A and B. Then you should draw the shear the shear and bending diagrams. And here you can just draw the shear because bending diagrams is required to analysis in normal stresses. So if you just have to calculate maximum shear in a, let's say at A, then you should take the most critical section. And to know what is the most critical section, you should draw the shear diagram and select largest B. And say then that this is my critical section. I will work in this section to get what is the most maximum possible shear stress I can reach at point A or point B or any value in your section. And of course, if you want the absolute maximum of shear stress, you should take, so since V, you have that tau is VQ over IT, okay? If you have a beam and they ask you what is the maximum, what is the point for which tau is maximum, then you should take several criteria. You have the section, you should determine in which section I have the maximum, okay? You can get this from the shear diagram. You should, for a certain section, you should determine, of course, maximum Q is known to be at the neutral axis. So in your section, you can take then the neutral axis and find Q max. For your I is a fixed parameter because it's for the whole section. But T, okay, T can be variable. Yani, what I want to tell you is to pay attention. In some cases, you have to consider several scenarios to know where is your max. What do I mean by this? We said already that Q is maximum at the neutral axis. Okay. But what if, for example, at the neutral axis, T is very high and you have another location with T is smaller? Then you cannot judge where is the maximum shear stress before doing calculation. And for example, if you have this cross section, you say it's true that Q is maximum at the neutral axis, but T is minimum here. So when T will decrease, tau will increase. So I should compare. I cannot judge which is more critical, this level or this one, before doing calculation. Okay. So the idea is, whenever I have a question, what is the maximum shear stress? Sometimes I cannot directly know. If it's a rectangle, it's the easiest case. In a rectangle, first I select the largest V in the beam. Then I say, because thickness is constant over my section, then of course tau max will correspond to V max and Q max, and Q max will take place at the neutral axis. So for a rectangular cross section, no need to do several of course, uniform cross section. It's not you don't have variation of the cross section with the beam. Okay. In case you have variation of cross section with the beam, also you should take different parts separately. So each part alone. So if we consider uniform beam first, it's a uniform beam. Then first I determine the maximum shear from the shear diagram. Then I move to my section. I say in this section, do I have variation in thickness? If no, then tau max is at the neutral axis. If yes, then I should take several sections of different thickness, okay? Because when the thickness will decrease, the shear can increase also. So I should compare, if you want, tau at different levels to determine at the two critical levels. The two critical levels here will be here and here. Okay. Why here, not here, for example? Because from this level to this one, the thickness is the same, but Q will increase as you go down. Okay. So this is the first critical side, and this is the second critical side. I should compare these two. Now, in case the thickness is minimal at the neutral axis, so no need to do any calculation, because already Q is maximum at the neutral axis, and if T is also minimum, then I can say, of course, tau is maximum at the neutral axis. Okay. And finally, also, you might have non-uniform beams. So if you have different cross sections, okay, you should also do calculation for each part separately, because the inertia can vary that. Okay. For uniform cross section, I is the same everywhere. But if you have different variation in cross section, then you should also then do the calculation of tau max in each part, and then select the most critical one. Okay. So now in this example here, they specified the section they want to work with. They want to determine the maximum, and not the maximum also. They want to determine shear stresses at specific points, at A and at B. Okay. So first I say I do the cut here. I determine the value of shear stress. All I have to do is to calculate AY, and from symmetry, because of symmetry, you can directly say that AY is 100 kilonewton and BY is 100 kilonewton. So you can directly say that from shear analysis, if I do the cut here, the shear is equal to 100 kilonewton. Now, once I determine the shear in my cross section, I move to my section to know what is the point of interest. First, I want to determine the shearing stress at A. So the first step will be to find the neutral axis of my section, determine its inertia about the neutral axis, and then I apply formulas. Okay. So at A here, when you do a cut here, so this is your cut. Please pay attention here. once you do the cut, what is the thickness you account for? When you do this cut here, you have that the shear stress at this point is equal to the shear stress at this one, okay? And because your cut is passing through two sections, then you have the total thickness here is 2 times 2t, because you have a cut at this level and at this level. So t that you should account for is 2 times this thickness, okay? And the q will be q of this part. And here, if I found my neutral axis, I can have two strategies. I can take the part above the neutral axis and do the analysis, but also it's easier maybe to take the part below the neutral axis, okay? So always select the easiest section to consider. Now, let us discuss in the problem what to do. Okay, so the first step is to locate the neutral axis. So we developed the technique in previous chapters. All you have to do is to divide your parts. Here, for example, they said, let me divide the part into 3 rectangles, and I have 2 of them will have same inertia. So I take this part as rectangle 1, and for these 2 rectangles, I have symmetry. So the inertia will be the same. So I can get the inertia of one of them and multiply by 2. So here you divide your part as we said, and you do your table. From your table, you can determine the location of the centroid, and you can determine the total inertia. Okay, so these steps you are already very familiar with. Now, once you are done, you move to finding the value of shear stress at point A. Here, as we discussed, we have 2 possible strategies. The 2 possible strategies are as follows. You can take, this is the cut, this is your cut, okay? This is your cut. You can say, let me take, to evaluate shear at this level, or I should take this whole section above the neutral axis. So for this whole section, sorry, above the section, okay? So, or I should take the whole section, the whole area above the section I did, or, but it's a complex area. Or I can say, if I take the lower cut, I have 2 areas, 2 rectangles, okay? Now, of course, the lower part is easier to deal with. Because you have, for the lower part, the formula is tau equal VQ over IT, okay? You can consider, because for the area, you have 2 parts and of equal thickness, you can just do the analysis per part, per rectangle. Because if you replace, you can say, if I name this rectangle 1 and this rectangle 2, and each of them has an area A, okay? So you have V times 2A times Y bar, both have the same distance from their centroid to the neutral axis. So 2 times A times Y bar over the inertia of the whole section times 2t. You have this thickness here. Since your cut is passing 2 times by this thickness, it's times 2. If I call this thickness here T1, if you want. So this is T1, and T1 equals to T2, okay? T1 is equal to T2. So it's over 2T1 or 2T2. Then 2 will simplify, and I can say I can just do analysis of this area, and then I divide just by this thickness, okay? This is what they did. And it's equivalent because if you take the two parts, you will have 2a and 2t, and 2 will cancel out. Okay, so now, of course, it's easier to work with the lower part. Let us work with the lower part. Then from the given, we have all dimensions required. If you go back to the figure, you have the thickness here, T1 or T2, which are equal. If they are not equal, okay, you cannot take only this rectangle. If you have T1 different than T2, you take the whole section, okay, then you take A1 plus A2, you consider A1 plus A2 times Y bar over times, of course, you do the formula VQ over IT. In Q, you take both areas, A1 plus A2 times Y bar. Y bar is the same for both, okay? Over I times the total thickness, T1 plus T2. But because they are equal, same area, same thickness, okay, then you can take only one part because 2 will be simplified as we have seen. So here in this formula, T will be 20 millimeters. I will be the inertia of the whole section. V is 100 kilonewton. And for Q, I should take Q of this area. So I should take A times Y bar of this area. This area is 20 times 38 millimeters. So A is 20 times 38. And concerning Y bar, to get Y bar of this area, I know that the centroid is at 19 millimeter from the bottom. And I already located my neutral axis from the bottom. So I found Y of neutral axis. So all I have to do is to take this distance, which is Y of neutral axis minus 90. Okay, so if I replace, in case of A, in A, I have QA is AY bar is 20 times 30.8 times, as we said, the distance from bottom to neutral axis, which is 114.6 minus 90. And now I will do the same for B. And for B, it's same analysis, but just the difference is that I have a different rectangle. So B is at a higher level. Okay, so if I go to my figures there, for the thickness, it's 20 millimeter. Now, for my area, it's a larger area, so I can expect that the shear stress at B is larger than the shear stress at A. So I have, this is 76 millimeters. Area is 20 times 76. And the centroid of my rectangle here is at 76 over 2. It's at 38 millimeter from the bottom. So now I can get the distance from the centroid to the neutral axis. So all I have to do is to replace into the formula here. So I have a tau at B. So here it's a typing error. This is tau at B equal VQ over IT. Q at B is area of B, which is 20 times 76, times Y bar, which is 114.6 minus 38. And then I plug in the formula Q by its value. V, as we discussed, is 100 kilonewton. Here, don't forget to get, here they are transforming units. They are putting V in a Newton. They are putting Q in. So here you have the value in millimeter to the power 9. Okay, you can transform it it depends on the final unit you want to decide on which unit you will use for your remaining parts. Okay, if you want to get your unit not if you want to get it in Pascal, you can convert all lengths to meter. If you want to get it in megapascal, okay, which is 10 to the power 6 Pascal. You can then select appropriate combination of units. So here, if you want, we go back to the value here. They kept T in millimeter, 20. Concerning the inertia, you got your inertia here. The value of your inertia is 33.725 times 10 to the power 6. Here I didn't mention the unit, but I think it's in millimeter because they didn't do any. Yes, it's they kept it in millimeter. Okay, so here, if you use I in millimeter 4, so as you can see here, if we kept I in millimeter 4 and we have the thickness in millimeter, V is in Newton, and the Q is in millimeter cube. So we kept all units in millimeter. We didn't do any conversion. What will happen is that you will get your result in a Newton per millimeter square. Okay, and we know that a Newton per millimeter square is megapascal instead of pascal. So if you keep your units in meter, you will get your final result in Newton per meter square, and then you will have a value in pascal. If you keep all units in millimeter, then you will get shear in Newton per millimeter square, and 1 millimeter square is 10 minus 6 meters square. So then tau is 10 to the power 6 Newton per meter square, which is megapascal. So this is why feel free to use the units you want. Just make sure to write the appropriate unit for shear. So if you keep all units in millimeter, then you will get your shear stress in megapascal. If you convert all units to meter, then the value you read will be in pascal. Okay, so this is the problems of this chapter. We are done with chapter 6.